Good afternoon. Thank you for joining us for our first speaker of our National Geospatial Speaker Series. My name is Nes Sandoval, and I have the great honor and privilege to introduce our speaker today. We have speakers who are here in the audience. We also have guests here in our audience, but we also have guests joining us via our Zoom link. And so if you have questions for our speaker, please use our function on Zoom. And then we will also be monitoring questions here in our audience as well. So today's speaker is Dr. David Messenger. He is the director of the Carlson Center for Imaging Science at Rochester Institute of Technology. Today he'll be talking about hyperspectral image analysis of medieval artifacts, applying a remote sensing technology to the study of culturally significant maps. And so with that, I would like to give him the floor.
Thank you, Ness. Thank you. Thank you for inviting me. My wife and I joke about this all the time. She's an anthropologist, and one thing she's taught me over the years is that a title of everything has to have a colon in it. Yeah. Social scientists and humanities people don't do anything without a colon in it. That was new to me as a physicist. So thanks again for inviting me. It's been a really interesting day so far. I look forward to the afternoon as well. And I welcome any questions you guys may have about this particular research topic. This is a little bit different than maybe what some of you were expecting. A lot of my research is involved in using advanced imaging technologies from satellites and airborne platforms for remote sensing. Over the last 5 or 6 years, though, I've been pulled into this other direction of what is called cultural heritage imaging. So using advanced imaging systems to study culturally interesting historical artifacts. And because this is a geo-slew sort of thing, I thought it might be kind of fun to talk about some work that we're doing on maps. Some really, really old maps in particular, maps that are 600-700 years old. This is largely, I'm going to present to you some work that's done by one of my PhD students, Steve I. He's now in the camera research group at Google. Grace Cow is one of my current PhD students. So the stuff that I do at the end, or I show you at the end, is really all her research. And this is largely facilitated by a gentleman by the name of David Howell, who used to be the head of heritage science. Previously, he was the head of conservation science at the Bodleian Library at the University of Oxford. He just recently retired a couple of years ago. The Bodleian Library is one of the world's largest libraries. It's also a library of record or something for the British government. So anything that's published in the UK has to be stored at the Bodleian. It's a really, really cool place to go. When I first went over there, David actually gave me a library card for the Bodleian, which is apparently a very rare thing. But it's kind of weird because you have to say this pledge out loud when you get there that goes back 1,000 years or something like that. And part of the pledge is that I pledge not to start any fires in the library, because apparently a long time ago it wasn't heated and stuff, and so scholars would burn little charcoal things, and it almost burned down several times. It's kind of funny. Andy Beebe is a colleague of mine at the University of Durham. He's a chemist by training. And so he leads a group over there that's really interested in the study of inks and pigments of historical manuscripts. And then Catherine Delano Smith is a research faculty at the University of London. Her research associate is Damien Bove. She's a cartographer by training. And so she is she's the editor of the journal Imago Mundi, which is one of the largest sort of historical map journals. How do I go forward? Okay, any thoughts?
Click on the slide. You should be able to hit. Yep.
Oh, there we go. Okay. So this is kind of a weird topic, right? But it's really the result of advances in technology and our understanding of how to use them. This allows us, as technology improves, as it gets smaller, as it gets cheaper, it allows me to use it for things that I wasn't really able to do before. So I can use these advanced imaging systems in ways that were previously not available to me. I can study objects that previously historical scholars would only visually look at, or maybe they would take a high resolution conservation photo in red, green, and blue or something like that. But now I can actually use these advanced imaging technologies to study them in more detail. And it really allows us to bring together these multidisciplinary teams to advance our knowledge of history in this particular case. So hopefully this will be of interest to you guys because of its map stuff. This is just a little bit of history. The first hyperspectral instrument that was really sort of production quality and actually flew a lot and collected data was this thing called Avaris. It was built by JPL in the 90s. I first worked with Avaris in 1998. This is what it looked like at the time, right? So this was the first ever hyperspectral system that was actually flown regularly, right? And so that's a guy, right? And so this thing is huge. It costs tens of millions of dollars. They had to modify a U-2 aircraft in order to fly it, so it flew at 40,000 feet, collected really big pixels, but it flew all the time, and it collected a huge amount of data. So if you're a hyperspectral person, I'll talk about what hyperspectral imaging is in a little bit. This is probably your first ever introduction to the technology. Of course, now I have this, right? So this is a headwall nanospec. I think you guys have one here. This is mounted on a DJI drone. We use this for precision agriculture. That thing is a little bit larger than this bottle of water. It's not as good as the Everest sensor, but it's still pretty good. And I can buy one for about 50 grand, right? So that allows us to do things like this, which is in the Heritage Science Lab at the Bodleian Library. This is a small little hyperspectral imaging sensor mounted on a rig with a plate that slides underneath it on which you can put documents and you can actually scan them. And so now this allows us to actually do hyperspectral image analysis, chemical spectroscopic imaging of historical manuscripts, artifacts, books, musical scores, maps, things like that. So it's only because this technology gets smaller over time, it becomes more affordable, right? So now I can use it in totally different ways that it was not dreamed of. When David first went to the Headwall guys and said, I want to do this, they're like, are you sure? Right now, they've sold 2 or 3 of these things to various libraries and museums around the world. So what is hyperspectral imaging, right? So my program is a little bit different than most. We focus on imaging systems. And so we teach our students a lot about the end-to-end imaging systems and what they can be used for. We always start with a normal camera, right? So everybody has one of these in their pocket. This image is in red, green, and blue. Why? Because the good people at Kodak, way back when they started to build cameras in color, they wanted the pictures to be a representation of what you actually saw. And your eye-brain system is sensitive to the red, green, and blue colors, parts of the visible spectrum. And so that's what it does, right? We don't have to do that. I can see in a bunch of other colors, right? If you've used any other camera systems like near infrared or NDB cameras or something like that, you can image things outside the human visual system, and that provides a lot of information. But if I want to image in lots and lots and lots and lots of colors, and the reason I might want to do that is to do better material specificity, separate out material differences, then I need to be able to do spectroscopy, right? So chemists have been doing spectroscopy on a benchtop for close to 100 years. There's a lot of different ways you can do it. The main thing though is that you have to do something like this. Thanks to the old band Pink Floyd, right? Everybody's probably seen this picture at some point in time, but this is literally what we do. In the optical path, you put a prism or some sort of a diffraction grating that spreads the light out into the continuous colors of the rainbow, right? And then I project that onto a focal plane. And by doing that, now I can image in hundreds and hundreds of colors. It's continuous, right? So there's a bit of I wouldn't call it a religious war, but there's a lot of differences of opinion between multispectral and hyperspectral. Most people will argue that it depends upon how many bands you have. I say that's totally wrong from my perspective, which is obviously correct. Right? You get a hyperspectral imaging system when you put a dispersion element in the path, right? I can achieve multispectral imaging by colored illuminance, by various spectral filters and transmission side. I can do that a lot of different ways. But it's not a hyperspectral imaging system to me unless I actually disperse the light, right? So I need to put some sort of a prism or a diffraction grating or something like that in the light path, right? So when I talk about hyperspectral systems, they are in exactly this sort of a setup. I've got some sort of a scan line, so I'm imaging something, and I've got a 2-dimensional detector at the back end, just like I have in my cell phone camera, right? The difference is that I'm only imaging in one dimension, right? The light goes through the optics and through a slit. It gets to this dispersion element that's aligned such that it spreads the light out in the perpendicular direction. And so when that light is projected onto the focal plane, I image in one spatial dimension and one spectral dimension. And so from an airplane, I'm typically looking down and I'm imaging this line that's right underneath me. So I image that line spatially, however wide my focal plane is, and spectrally, however tall my focal plane is. I read off all that data, the airplane moves forward, I collect the next line. The airplane moves forward, I collect the next line. And so I have to have some relative motion between the platform and the object in order to build up the 3-dimensional cube, right? So now I've got 2 spatial dimensions, one because of the width of my focal plane, one because of the motion of my platform, and that 3rd spectral dimension because I pass it through this dispersion element and I get the spectra like this. The spectra can be very complicated, right? They have hundreds and hundreds of channels. Mathematically, I think about them living in an n-dimensional space where n can be 3, 4, 500. I use some advanced mathematics and statistics and manifold learning and graph theory and all these kind of crazy things to try and figure out how to pull information out of that. I'm not going to talk about any of the math behind what we do. Suffice to say, if anybody wants to talk about mathematics in hundreds of dimensions, I'm happy to hang out later on. What I'm going to focus on here is the results of what we can actually do from that process. So this is how the image is set up. This is just another image of David's lab. This is actually what's called a palimpsest. So this is a piece of manuscript. So it's a piece of parchment that was written on and then scraped, right? So then somebody wrote something on top of it. So this is a 14th century palimpsest imaged in his lab. This is the camera system. This sort of box back here is an illumination. It's very bright illumination that only typically illuminates a line. One of the problems we have with these things is conservators don't like you to shine bright lights on these things, right? That's bad for the parchment, particularly if you want to illuminate in the ultraviolet, right? So it's higher energy and it does bad things to it. So you have to be very careful about how much illumination you throw down. So the camera's mounted on this rig. That's pretty stationary. It can go up and down to change your resolution. And then the object sits on this little table, and this table is motorized so it can slide back and forth. So to image something like this takes about 5 minutes, right? Under normal resolution conditions sort of thing. I'm going to talk about these two very large objects, the Guff map and the Selden map. Because they're so big, they were not imaged in this particular manner, but you sort of get the idea of how we do this.
Curiosity question.
Yeah.
Is that a string of LED lights around it?
This
There's
thing?
a white cube
No.
that looks like it.
Anybody know what this is? It's a weighted rope. So parchments curl based directly on the temperature and the humidity and the environment they're in. And so the camera has a very, very narrow depth of focus. And so we try to keep them as flat as possible. So it's a technology, I believe, that was originally designed for curtains. So they have these weighted ropes with lead balls stitched into them.
Yeah.
And that's what we use a lot of those things.
Just
Yeah.
follow-up question on that. So what about the impact of light on the wall?
This?
And yeah, the light on the wall as well. You can see the reflection of
Yeah,
light.
so this isn't a great setup. And when I first got there and I saw how David had set this thing up, I'm like, yeah, you shouldn't do this way. We do our best to try and calibrate all those effects out, right? But at least for this imaging setup, getting to absolute reflectance wasn't a real requirement. So I wasn't too worried about it. Normally, we drape black stuff on that wall and things like that. And so you would try to make it a little bit better than this, right? But that's one of the problems when you have non-imaging people buy advanced imaging systems and try to use them. So this is what you get when you image in hyperspectral imaging. So I'll talk about what this is in a little bit, but suffice to say there's 3 points of interest here: some green pigment, some red pigment, and some parchment. I'm imaging as a function of wavelength. This is a silicon-based detector, so it's only sensitive out to about 1,000 nanometers, right? So I'm interested in the V-near part of the spectrum, visible and near infrared. If I do my calibration correctly, then I can get the data to absolute reflectance. I probably can't do that correctly, but it's probably close enough. So this is a number between 0 and 1, which reflects the efficiency with which the material reflects that light at that wavelength. And you can see this is massively oversampled. There's several hundred measurements here that describe the reflectance of, in this case, the blue is the sheepskin as a function of wavelength. The fact that it is relatively flat in the visible part of the spectrum, this is roughly blue, green, and red, is why this sort of looks whitish. This is the green spot, so it's got a very significant peak at the green wavelengths, which is why your eye perceives it as green. This stuff is very bright in the red, which is why your eye perceives it as red. But you get these data points for every pixel. There's, in this case, about 300 measurements of what the reflectance is as a function of wavelength. Mathematically, we treat the data structure as a cube. We treat each individual measurement as a vector, a 300-dimensional vector that lives in this high-dimensional space. We typically throw out the spatial information because the resolution is not really great enough that I care too much about that. We typically only process the data in the spectral domain, although I'll show you some work at the end where we're trying to get beyond that very bad assumption. What can we learn from it? Codicology is a cool word that I only learned a few years ago. It's basically the study of the object as an object, right? So what were the materials that went into making it? What were the tools that were used? How was it modified? How was it changed? It's not so much about the content of the object, right? If I'm studying a medieval manuscript folio, the historical scholars want to know what the words say. We're more interested in how was that thing created, right? So we can learn about the codicology. We can learn about the materials, techniques, tools, possibly the timelines, how was it changed or modified over time. In particular, we want to look at specific features on these maps. And can we see global patterns? I'm imaging, which means even though I'm processing each pixel individually, I want to identify, are there patterns? These things, unlike going out and flying a drone over some farmer's field or something, these things were made by humans. And the spatial information is inherently the information that I care about, right? So I'm looking for large-scale spatial patterns in these things. Identifying and reading faded text is something that we haven't really cracked a nut yet on this one. We haven't spent a lot of time on it. The estimates are that at least 30 to 40% of all the text that was ever written on these maps is gone, faded, sometimes accidentally, sometimes intentionally. The gentleman that owned the Guff map, so somewhere in the 1600s or 1700s, something like that, the text was starting to fade, and somebody convinced him that if he took a sponge and dabbed it on red wine, and then he dabbed it on the map, it would increase the contrast of the ink. That actually works, but only for a few weeks, and then you get a red wine spot on the map. And so we're trying to figure out ways to try and penetrate through that. Okay, so I'm going to talk about two things, two artifacts, the Guff map and the Selden map, both named after people. These are both objects that are in the Bodleian Library. They're both labeled as treasures of the Bodleian Library. They are extraordinarily rare. They're extraordinarily fragile. They have interesting stories. So the Guff map study is part of a large collaboration of historians. It's led, like I said, by Catherine. And basically, they feed us questions, and then we try to answer them. Okay, so we're not really driving this. We're trying to be more reactive to the questions they have about the map. And when I show you the map and talk about it, the Guff map in particular, there's a lot of unknowns about it. The Selden map is a little bit different. The Selden map is kind of interesting, mostly because it was lost. People knew about it for a long, long time. They knew it existed, but nobody had seen it in like 50 years or 75 years or something like that until somebody found it, literally in like the back of a closet in the library. The objects are very, very different. The Selden map is on paper, it's printed with watercolor, or it's painted with watercolor. The Guff map is on parchment, done with pigments. They differ by several hundred years. And so one of the things I'm always interested in is if I develop techniques to study this, algorithms, do they translate to this, right? In other words, are there robust ways of thinking about and processing the data that I can apply to multiple artifacts, or do I have to start over every time I have a new thing, right? Okay. This data is different than remotely sensed data. I consider it extraordinarily high resolution, 1/10 of a millimeter, right? Which to me is crazy high resolution. That means the data looks very, very different in the cloud. I can run statistics against this data, but it really doesn't apply. The data are not Gaussian, right? So I can compute covariance matrices and do Gaussian maximum likelihood, all that sort of stuff. None of that really applies here. It'll give me an answer, but it's wrong, right? And so the question is, how do we leverage how the data look to build algorithms that can correctly process them? Okay, the Guff map. Somebody has a question in the chat. Should I be looking at that?
It's not a
Okay.
relevant question.
The Guff map is very interesting. I'll show a picture of it here. It's the first map of an island that sort of looks right. And you'll see when I show you that it looks like Great Britain, right? And it was originally created in approximately 1390. They know that by the place names, this process called paleography, sorry, not paleontology, those are different. It's very precise, right? And they don't know how they did it, and they don't know why they did it. And they don't know what the map was used for, but they know that it was used for well over 100 years, and they know that it was modified over time. And in particular, it was modified in ways such that it didn't look like it was modified, right? They were making corrections to it. They were adding information. They were rewriting when the ink faded, but they wanted to do it in ways such that it wasn't obvious that somebody went in 50 years later and made a change. Dates originally from about 1390, used for 100 years. It's not just an outline of the island. It's got over 600 places and names of places and features on the map. And this is what the historians are really trying to study is what do these things do? What do they teach us about both map making at that time, as well as what was the cultural knowledge at the time? Why would somebody want a map of the entire UK in the year 1400, right? This is what it looks like. It's pretty good size, about 1 meter big by ½ a meter. You'll see a seam here. This is one of those amazing things that they have no idea. The right, roughly 3/4 is sheepskin, the left is lamb. They made the parchment before they started to draw the map. How many people have tried to draw a map with directions to your house, and then you get to the edge of the paper and the scale gets all compressed because you ran out of space, right? They didn't do that here, which means they knew how big the island was. They knew the scale they were going to draw it, right? England is up here, Wales, Scotland, Europe. They think at some level this is water damage. They think it was rolled up and sort of stood on its end and it probably got wet. We tend to throw all this data out just because it's very complicated. This is the medieval period. People did weird things. The top of the map does not point to north like we normally would now. At that time, the top of the map pointed towards Bethlehem. Okay. There's fish in the ocean. This is the representation of a shipwreck with a little guy trying to flee it. There was some famous ship that was coming from Norway to Scotland that crashed at the time or something like that, so they tried to depict it. Somewhere down in here, there's supposedly some writing that says this is where King Arthur landed, right? It's a medieval time period. Things are weird. But you can see there's a lot of detail on this map. Yeah.
Is there any significance that the map seems remarkably familiar? The islands seem wildly out of scale.
No clue. Probably just because they didn't have access to the islands, particularly up around Scotland. They didn't have a lot, I'll get to that in a second, but they didn't have a lot of information about Scotland, nor did they care, which is really kind of the cultural perspective, right?
Well, that's understandable, right?
Yeah. But
It's
you
an
can
English
see,
map.
but a major feature on the map is this thing right here. This is Hadrian's Wall, right? So this is the Picts Wall built by the Romans to separate England from Scotland. And when we get into some of the analysis, you'll see a dramatic difference between north and south of the wall, right? That was their boundary. If you zoom in, you can see things like this. So every town is represented by a little building. The green stuff is water, canals, rivers, things like that. The size of the town is based on how big the building is and what the building looks like. So like these two towns are roughly the same size, but this one has a church. This one probably has some sort of a castle in it, right? This town is bigger, these towns are bigger. The names in black are typically the name of the town. The names in red are typically like the region areas. This part is the kicker though. All these straight lines with these labels, those are the distances between towns. So if I were to go to you guys and I were to give each one of you, you guys heard this morning, if I were to give each one of you a piece of paper and a pencil and a horse, and I said, I want you to map out the entire state of Missouri, and I need to know where everything is and the distances between all the towns. How would you do that? Right? There's a lot of overwriting in it. You see places where like up in here, there was probably writing underneath and it faded and they rewrote on top of it. There's places where the writing is just faded completely. There's a lot of that sort of stuff where you expect to see something, it looks like it was erased or something like that. So the question is, how did they make this thing? The Selden map is very different. 17th century watercolor on paper, right? Of unknown origin, sort of known purpose. Although it's largely a piece of art, it was meant to hang on the wall. It's actually a very accurate navigational map. So this is a much larger area, obviously. So this is China, Korea, Japan is over here, kind of in the wrong place and definitely not the right shape. Asia down here, Java, Ambon, something down here. We don't know what that is really. This has a lot of different colors, right? So it's a lot of different types of watercolor. If you zoom in though, one of the key things is that up here in the top, there's a navigational rose and there's a scale bar, right? So if you look at the history of navigational charts, this was a technological leap for the Chinese. This map has an interesting history. It was probably captured off a ship by a British pirate who then got back to London, sold all of his loot. Mr. Selden bought this as well as a bunch of other things. When he died, he gifted all of his stuff to Oxford. It hung in the Oxford, somewhere in Oxford for a long, long time. And then Sir Edmund Halley, he looked at the map and he said, nope, this is wrong. So they rolled it up and they put it away. It turns out it's right, It's just that the Chinese had a better understanding of map projections at the time than the Western world did. So the map is actually very accurate. If you zoom in on it, you see navigational routes. Let's see, these little signals are like directional headings. You see these circles with like this stuff blowing off the side. Those are typically either currents or wind. So it is an active navigational map, how to get from point to point. If you look, where is it? You can barely see it, but there's writing over here, which tells you how to get to places off the map, right? So they knew a ton about this area, and a lot of that is captured on this map. You can also see, interestingly enough, from a pigment perspective, things like this, right? They probably screwed up Korea. And then at one point in time, they went back to try and fix it. These also look like edits down here. There's definitely some edits around Taiwan, right? You can barely see it, but there's a little circle here. They thought Taiwan was bigger. These circles represent major cities. They thought there were 3 major cities on Taiwan, and at the time somebody went back and changed it. Okay, so those are the things that we're going to be looking at. Those are some of the questions about the things that we're going to try to solve. So let's go back to the GUF map. So this is the map in its case. It's stretched out onto a wooden frame by with very thin silk. It's sealed in this case, which I believe is filled with argon, some sort of inert gas. This guy, good friend of mine, Nick Malia, he's in charge of all the maps at the Bodleian Library. So around 2015, there were a bunch of people studying the map, and there was this mini academic battle, a bunch of publications arguing over the purpose and the way the map was created and stuff like that. So they all got together and they went to the BOD and they said, hey, why don't we take this thing out of the case and let's actually study it. So they took it out of the case for, I think, roughly 3 days. They did a laser scan of the front and back. Andy did a bunch of point Raman. Raman spectroscopy is great because you can get to molecular characteristics of the pigments. You can get to real chemical analysis, but you can't image in it. So we have 70 Raman points. Then they imaged it in hyperspectral. It's a very large object, and so they had to make a choice when they imaged it in hyperspectral. Do we image the entire thing at low resolution, or do we focus on very specific parts and do it in high resolution? They chose the former, and so we have relatively low resolution imagery of the entire thing. When they did it, because of its size and shape, they had to break it into these 6 tiles. So you can see there's overlap here. They kind of screwed it up when they tried to pull the illumination out. They didn't do a very good job. So it's a little bit brighter on this end than it is over here. So we've had to normalize out a lot of those differences, some of the details of the whole thing. But it was done in about 300 spectral bands, spatial resolution of about 1/10 of a millimeter. So it's pretty good data. It's a processing challenge though, because it's a heck of a lot of data. And so how do you build products that fold in all of the information across the map is a challenge. You can find some interesting things very quickly. So this is one of those chips that sort of is Scotland. This is just the red, green, and blue from the hyperspectral imagery. If I say principal components analysis, people sort of know what I mean, right? So it's a statistical thing where I can analyze the data, and I'm trying to come up with, it's a very unsupervised sort of very, blind approach to doing data analysis, but I can highlight material differences. This is not a particularly interesting thing. Well, it's interesting, but not useful, shall we say. If I do that, remember I said this seam was sheep on one side and lamb on the other? You can see the rib marks from the lamb. So the lamb was really skinny. And so when the skin was stretched over it, that had a chemical change to the lamb skin that you don't see in the sheep. So again, it's interesting, but not useful, but it does show how you can get at some very, very subtle signatures with hyperspectral imaging. This is another example. Can we find subvisual text? So this was, again, not something we were trying to do. It was just sort of, I was playing around with the data when we first got it. There's actually a little blotch here. They had told us they were interested in some faded text in this area, and particularly some red text that they thought had faded away. So all I did was I did a simple spectral signature matching algorithm. I grabbed a piece of red pigment from someplace and I ran it across this chip to try and see if I could find any text that wasn't there. What I found though was actually underneath that little blotch. So that blotch, that's not where somebody tried to erase it. That's actually a spot on the sheepskin. This is the high resolution conservation photo. So this is like a factor of 5 better in resolution than the hyperspectral. But in the hyperspectral, I can clearly see that there's words here. There's letters here, right? This is a map. They know what that town is. They can't read that, but that's not the name of the town now. And so at some point in time, this town got renamed and they don't know why, and they have no other historical record of it. So these are some of the sort of interesting things you find when you're poking your way through this data. Getting back to your question. So this is the current working theory about the map. That in the late 14th century, they did the whole thing. They drew the outline of the entire island of Great Britain, and they filled it in with some level of detail, right? With whatever they knew. You get to, 25, 30 years later, they decide they don't care about Scotland. And so they start making modifications to the map south of Hadrian's Wall. Okay, so there's a lot more detail here. And then 50 years after that, I believe it was about the same time that London was starting to emerge as one of the major commercial centers. They focused all their efforts on the area right around London and sort of Southeast England. So this is the sort of working theory for the evolution of the map over time. And the historians are just constantly asking us questions that can either verify or contradict this theory. Okay, so that's basically the game that we're trying to play. What we did, first of all, was we wanted to look at the global scale of the map instead of doing point analysis. So we tried to analyze the red and the green pigments because those are the most dominant things. The black ink turns out to be a difficult problem that we've worked on, but I don't have any good results on. So I'm not going to show you that. Remember, the red is the writings and the town signs and stuff like that. The green is the water. And so what we're trying to do is analyze and see if there are spatial patterns in the distribution of these pigments and changes in those pigments across the map that might indicate something about how it was made and changed. There is reason to believe that the water was done at different times. And I'm not going to talk about the algorithms here. We're using, essentially for any of you that have done hyperspectral analysis, we're extracting end members, trying to understand the material diversity, doing spectral and mixing, classification. These are all very traditional standard algorithms. I'll show you some machine learning stuff at the end. So again, this is the map. This is what it looks like. So what I'm going to show you first is our pigment classification map of the green pigments. I think it's green. So in what I'm going to show you, the colors represent our estimation of different material classes, but only amongst the green pigments. So we took everything that wasn't green and we just ignored it. And then within the green pigments, I tried to figure out how many different types of green pigment are there and where are those different green pigments located on the map. No, that's right. It's green. It's green, but it's internal to the island. We didn't worry about the ocean part for this. I'll show you that later. So in this, every spot that's blue means that we believe that those are all the same green pigment. Every spot that's yellow is the same as the other yellow spots, but it's different than the blue. Okay. So this is interesting because, first of all, there's clearly a separation north and south of Hadrian's Wall. But there's also a lot of interesting information here. You see a lot of these where they get somewhere into the inlet on the river and then they change the pigment. Right? You see this in a lot of these things. Here. There's some indication and some historical precedent for the fact that these were probably very obvious distinctions at the time. And they probably had some meaning about, like, this is where you can cross this river on horseback at low tide or something like that. There was probably very significant meaning to these things because you see them all over the place. This is part of that water damage and the fold structure down on the map, so we kind of ignore that. I should say though that this algorithm is probably a little too sensitive. So as they're mixing pigments in their little jar and they're applying them on, if it gets a little bit thin, maybe they add a little sand or something to it, and it's really all done at the same time. This may be a little bit too specific to be truly meaningful. So a lot of these, where you see differences like here between the blue and the yellow and the green, we probably don't really believe that, right? But that's where the historical scholars come into play. Let's see, I skipped that. So this is the reds. So remember, the reds were used to draw those little towns indicating where places were and to draw what they call the cartouches, the writing that refers to a place name, not a city name. There's a lot of blue towns throughout the entire place. But when you get up into here, now you start to see what we're calling a green. So this is a different type of red pigment. There are some sections like over in here is where all these things that are colored yellow, those were probably very different. So at some point in time, this area became important and they went in and they filled in a lot of towns, right? And the part, so this sort of open circle here is London, right? But you can see there are very distinct patterns in these things that give us an indication that, first of all of the big label writing was probably done at once. But when they went back and looked at the individual towns, they made changes over time. The green pigments in the ocean, somebody had some theory that, is there copper in the green pigment? So there's only a few ways you can make green, right? So the question was, is there copper in the green pigments, particularly in the outline around England, right? So there were a few of the Raman analysis that identified indigo enriched green. So that's another way you can make green. But the question is, can we actually do this with the hyperspectral data? I know I can do it with Raman. I just don't have Raman data over the entire thing. So can I do this with the hyperspectral data? It turns out you can, otherwise I wouldn't be showing it to you. So if I take two spots where I have Raman data and I know one of them is copper and one of them is indigo, this is what I see for that reflectance spectrum, right? So I get a big peak at the green, that's why they look green. But for one of them, I get this very sharp rise in the infrared, and for the other one, I get this deep valley, right? So this is copper. If I see this feature in here, then I know that there's copper in that pixel. If I see this feature, I know it's probably indigo. Okay, this is awesome. Simple things are always easier to do, so we do a very simple thing. I'm going to take a pixel, a point here for every pixel, and I'm going to ratio it to this one. Because I know if the ratio is either this one's always a little bit higher or roughly the same, and this one is the opposite, then I can build a map. I can tell you for every green pigment on this thing, whether it likely has copper in it. We have to do some other stuff, normalize out brightness variation and things like that. But in general, it's really easy to do. And this is what you get. Dark red thing, the blue stuff is not green, we ignore it. Dark red here on the scale means, yes, I believe there's copper there. Yellowish, greenish stuff means no, there's not. Again, Hadrian's Wall is right around here. Somebody probably went in later on and redid the outline of England in that second or third phase of the map's history. Interestingly, they probably went through and touched up some of this stuff too. Now, if you look at it in the visible, you can see that it's darker there. But the question was, did they just go on and slap on another level of paint, or was it actually a different type of green pigment? So this is basically the type of stuff that we've done with the Selden map. I'm going to move a little bit quickly here so you all can leave. Or with the Guff map. The Selden map is a little bit different. There's not as many people studying it from a scholarly perspective. So we're basically trying out algorithms to see what we can make work, see if we can try to unearth some interesting features about it. Again, it's pretty big. You know, it's like a meter, just a little bit bigger, a meter by a meter and a half. It's imaged in like 15 or 16 chips. They actually did image the middle, but for whatever reason, when they transferred the imagery to us, it didn't make it. So we don't have that. Again, we're trying to look at the pigments within the map. If I know there's green pigments and I know they specify things like the boundaries of land and water, were they all done with the same jar of green pigment? Or can I somehow try to figure out differences that tell me something about the evolution of this map? So again, it's standard hyperspectral stuff. I'm going to do spectral unmixing and member analysis, blah, 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 all that sort of stuff. I'm happy to talk about that stuff later if you want. So again, this is the class map that we get. So the gray pixels are pixels that I ignored. I'm only interested in the green pigments here, which specify water. 2 pixels here that are the same shade of this light blue, they're probably the same pigment. Okay, so if I look at this, so this is the Ming Empire. Even though this was a navigational map with explicit instructions for how to sail on the ocean, they spent a lot of detail on the inland part. It's a little unclear why. But there's a clear distinction between north and south. Some people interpret these as rivers. Some people interpret them as sort of province boundaries, right? Which are naturally along a lot of rivers anyway. There's a clear difference between the ones in the north and the ones in the south. In particular, whatever these guys were, they're the same thing as this big blotch down here. Almost certainly. No idea why. So we do the same sort of processing and we can come up with a bunch of different sorts of analysis, right? There's a clear spatial difference in the green pigments that were used here. They're very similar to this. They're very different than a lot of other places. I don't know why. I don't know anything about historical maps. That area around Korea that was clearly filled in, over here, we've labeled it as all this purplish and blue stuff. Oh, by the way, they made a correction down here with probably at the same time. Right, so the current theory is that they had originally drawn an island here. They thought there was some landmass here, and it turns out there wasn't. Somebody came back at some point in time and said, yeah, no, there's nothing there, actually. Fill it in with green, right? So these are the types of things that we're trying to learn from these maps, using, in this case, very traditional hyperspectral analysis. One of the challenges we have here is that I don't know what the answer is, right? So as a scientist and an academic in particular, I like to run experiments where I know what the answer is, or I can at least isolate all but one variable, right? We have no knowledge of the actual pigments that were used in these things. We have ideas from historical readings and stuff like that, but I have no way to optimize my algorithm to make sure that I get, say, a high per class accuracy. Right? For those of you that have ever done classification problems, you're going to run it against some data set for which you know the label on every pixel, and you're going to try to maximize per class accuracy or overall accuracy. If you're doing target detection, you're going to try to maximize your probability of detection. Right? I don't have any of that stuff here. So one of the things that we do a lot of, which I'm not really presenting here, is that we run a number of different algorithmic approaches on the same problem. And if we get the same answer all the time, then we believe that that answer is a little bit more robust. If I get a bunch of different answers, then I know that I'm doing something wrong, right? So that's another way we try to validate what we're doing. So this is all great. Hyperspectral people have been doing this for a long time. You can debate how to do material difference estimation and all that sort of stuff, but this technology sort of works. Over the last several years, we've had this revolution in neural networks, learning frameworks, artificial intelligence. None of that is new. Particular for you young students in the room. None of that stuff is new. That's all been around for 30 years or something like that. We just now have enough computers and enough labeled data that we can actually use it, right? That stuff is interesting though, because fundamentally what a convolutional neural net or any sort of machine learning framework is trying to do is trying to develop an approximation to a nonlinear function that you don't know, right? That's fundamentally what it's trying to do. These data are inherently nonlinear and non-Gaussian, right? This is very complicated data. If you look at it in the spectral domain, you see a lot of weird shapes. So I want to develop some sort of algorithm that will leverage that nonlinear nature of the data. Years ago, I sacrificed a large number of PhD students to the study of manifold learning algorithms. This was called machine learning at the time. It's not now. But effectively, a manifold learning algorithm is trying to develop a nonlinear transformation that takes nonlinear data and moves it into a linear domain such that I can run linear algorithms on it. And you do that by developing what's called a graph theory model of the data. So you're point sampling the nonlinear structure, you're building a matrix that describes that structure, and then you're processing it. Now, it turns out some very smart people, not me, have figured out how to combine those two things. So I can represent the data as a nonlinear manifold, and I can build a convolutional neural network that will approximate that nonlinear function at the same time, and it will produce labels. Okay, so I can do classification without having any of these assumptions about the data. So in a traditional graph theory framework or a manifold learning framework, if you want to learn more about this, I'm happy to talk about it later. You take your data, you build a graph, so you're representing every point as a node in some high dimensional space. You connect it with edges if they're close, however you define close, blah, blah, blah. You build this thing called the adjacency matrix and a Laplacian. which is some mathematical manipulation of that. You do an eigenvalue decomposition on that, and then you run a classification in the new space. So you're ultimately running a classification algorithm, k-means, GML, SVM, whatever. Here, what we're trying to do is we're lumping all of that stuff into a learning process, which basically means I need some part of the data for which I have labels, for which I know what the answer is. So I tell my grad students to spend 50 hours go labeling every pixel, right? So what she does is she labels a bunch of the data. She pushes it through this pipeline where she learns how to get the right labels on the output. And then you take that approximation for that nonlinear function and you apply it to new data, right? I'm okay with having to label parts of these maps. I just don't want to have to label the whole thing, right? This is what you get. This is a zoom in on part of the Selden map. These algorithms are extraordinarily slow, which is why you can only run them on something like this right now. Otherwise, it takes more than a day and the student is just sitting around twiddling their thumbs. So you train it on this little area and then you test it on this big area, which critically you believe has the same distribution of materials in it. And you can get really good results. So these are all a bunch of other ways to do this. This is from a paper that's actually not even been published yet. It's going to be presented next week at a conference. The critical thing here is that each one of these different weird acronyms is a different way to do the same step in that process. How do I build the graph? And the idea is if I've got 15 different choices of how I do this, which one gives me the best answer most of the time? We haven't completely solved that yet. I just kind of wanted to show this to you guys from both the Selden map, where you can show that if I use spectral angle distance and a k nearest neighbor graph and a density weighted or a natural nearest neighbor graph, two different things that are very mathematically complicated, I can get better results than if I use a baseline classification. Right? Now this one took probably less than 10 seconds to run, and these took 6 or 7 hours, right? These maps are 100-year old. I don't care if it takes me a while to process, right? You can do the same thing for the Guff map, it turns out, and this is the important part. You can do the same thing for a totally different artifact from a very different time period, used with different materials and tools, and basically get the same result, right? So what we're trying to get to the point of is I have a standard workflow for how to process this data, right? When you guys fly your hyperspectral sensor over some agricultural field or something, you know how you're going to process it, right? Your general workflow to get all the way to the end is pretty solid, right? For these things, because each one is very different, we don't have that workflow yet. And so what we're trying to develop are methods to get to the point where, using exactly the same techniques here, I was able to still improve my performance over a baseline output. So this is very much ongoing work because the student hasn't graduated yet. Keep going. Okay. So this is a very different use of hyperspectral technology. Hyperspectral technology is pretty common nowadays, right? I can pay a company to come fly a hyperspectral imaging system on an airplane or a drone, whatever. But because of the advent of building little ones that are reasonably good, it opens up a whole new world of what I can use them for. We see companies that are putting hyperspectral imaging systems in their manufacturing lines to do quality control, right? We have a bunch of students that work at Corning Glass just down the road from us. Why? Because they're building huge sheets of Gorilla Glass and they need to make sure that they're good, right? So the fact that I can do this to get at chemical signatures in materials, which I've been doing from airplanes for 20+ years, now the fact that I can do this in a lab-based setting, it opens up a whole new world for how I can do this stuff. And in particular, with this study of these historical things, it allows me to partner with historians and scholars, and in some cases, archaeologists, to try to understand, use this technology to understand historical context so that we can learn more about these things from the past. There's a lot of work to be done. This is much large. We have a pretty large research area in this effort. I have a pretty significant NEH grant to build multispectral imaging systems to be deployed in museums and libraries, only focused on manuscripts. We have an ongoing research project with the National Gallery of Art to study how hyperspectral and other sorts of imaging technologies can be used in the conservation and essentially pigment mapping of very classic works of art. There's a lot of cool stuff that could be done here. I just found out on Friday that it looks like, against all odds, they're going to take the Guff map out of its case again. I requested this several years ago and they said, yeah, no. But somebody convinced them to do that again in June. And so we're going to be going back, not doing hyperspectral analysis, but doing very high resolution multispectral imaging of parts of the map to try and answer some very specific questions for the historians that are studying the map. So this is one of those things of constantly iterating on the same object to try and further our understanding of it. So that's it. This is me. Send me any questions, particularly if you have any questions about the math behind any of this stuff. We have built this cool thing. It turns out there's some faculty at the University of Rochester who are more on the historical medieval studies side of this. And so we built a cool little collaboration between the two universities. We conveniently call it Archive. And it actually stands for something. If you're interested in the use of imaging technologies to study historical artifacts, you can go to this webpage, and we actually have a Google mailing list. We have a meeting twice a month, every other Friday. We have speakers from all over the world present, typically 15, 20 minutes, stuff like that, on research that they're doing in this area. It's mostly imaging of historical artifacts. Sometimes there's some other interesting things going on. And this is, I don't know if there's any undergraduates in the room, but I'm always looking for really good PhD students to come into my program. Shameless plug. Thanks.
We have about 15 minutes for questions from our audience and also questions from our Zoom audience. And so we'll facilitate that. I'll start off first. Can you talk a little bit about the time that goes into actually the analysis? Are we talking weeks, months? What's the time commitment?
Sure, there's lots of different aspects to that. Let's talk about the Guff map because we've done more large-scale interpretation of the Guff map. It's millions of pixels, right? And so the question is, do you want to study a part of it or do you want to study the whole thing? Do you want to look at a region? Do you want to look at the whole thing? Are you trying to develop a spatial understanding of the entire thing? Am I trying to focus on sharpening this very particular part of it, right? If you want to process the whole thing, it's hours and hours and hours, even if you are using these traditional methods that don't take any time at all, right? So if I gave one of you guys an image that was, 100,000 pixels in NV, and I said, I want you to cruise a class map. Okay, fine, I'll be back in 20 minutes, right? For this thing to do that, remember, there are also different images. There's completely different images. They were not well calibrated. So in order to do all that processing and then merge all the results such that you have a global answer where class 5 is the same in each one of those chips, it takes a long time. I mean, a dedicated grad student, a week or two to do that. For the machine learning stuff, it takes forever to process that little chip, hit the button overnight. I'll look to see if it's done when I get up in the morning. Any of you guys doing machine learning, you know the gig.
You image anything aside from maps, any other sort of like cultural artifacts?
Yes, maps are a very small part of what we do. Historically, these are the only two maps for which we have hyperspectral data right now. Our team was involved in imaging what's called the Waldseemüller map, which I believe is at the Beinecke at Yale, which is one of the earliest maps of sort of the New World. There's another big map, I forget the name of it right now. We've only done 3 or 4 maps. Maps are hard, they're big typically, right? And so it's really hard. We have a project right now where one of my faculty members is going to Verona, I think, in the spring to image a globe, which will be very interesting. That's a globe that's actually a sphere that had parchment pasted onto it, and it was palimpsested, so they scraped off part of it and changed it. That'll be a very difficult challenge. The vast majority of this sort of stuff we do are manuscripts. So a palimpsest is a piece of parchment that was scraped, because parchment was hard to make. It's really difficult to make. So people would scrape it, and then they would resell it, and somebody would write another book on top of it. There's some estimate that, I don't know, hundreds and hundreds of thousands of palimpsested manuscripts in libraries and archives just in Central Europe alone, because recycling parchment was such a common thing that pretty much any manuscript from this time period, you pull it off the shelf, there's probably a 1 in 5 chance or something like that, that it's been palimpsested, right? We are part of an ongoing project at St. Catherine's Monastery in Mount Sinai, which is the oldest, I believe it's the oldest continually active library in the world. 10 years ago or something like that, they were doing some remodel or something, and they took down a wall and they found a room full of manuscripts that they didn't even know existed. And so one of our colleagues at what's called the Early Manuscript Electronic Library, he won a very large grant to install a multispectral imaging system there to image all of those things. That data is publicly available online through UCLA, studying those sorts of palimpsests. When they get very difficult things to deal with, they send them to us for advanced data processing outside of their standard scheme. Yeah, we largely focus on manuscripts, though, are more, we know how to do that. I know how to build an imaging system and I know how to process manuscripts. That's more of a, like we were talking earlier, that's more of an engineering thing, right? How do I image thousands of pages, right? So like I have a proposal right now in front of the Croatian government to build a spectral imaging lab at Dubrovnik, which has one of the world's largest collection of medieval manuscripts because they weren't bombed during the war. But they're fading, they're going away, right? And so we're trying to come up with ways to build more of these imaging systems and get them in more places just so we can start turning that crank, right? Where the science comes in is when you're trying to do more quantitative stuff like this. The artwork thing is huge, right? Trying to understand pigment mapping in historical artworks, that's a real big problem. And that's an incredibly difficult scientific question as well. Other way more challenging things, we're trying to build an imaging system that will image all of the unrolled Herculaneum scrolls. So the Herculaneum was that library that was buried under Mount Vesuvius. And so those are all papyrus written with black ink, but they were rolled up. And in the 1700s, some very smart person in Italy created a machine that would unroll some of them. So there's like 3,000 of these things that have been unrolled, but they were burned and buried in volcanic ash. And so they're very, very difficult to read. The Bodleian has a couple, and they were imaged with this hyperspectral system, and we were able to pull out a significant amount of text in them. And so we're working with folks at the University of Kentucky, which have, I think, a MacArthur Foundation grant to go image the 3,000 or whatever that are in Italy. Again, that's more of a process. Once we understand the chemistry behind these things and what imaging needs to be done, we think we can turn the crank on that for a vast majority. But there's a lot of stuff out there that could benefit from this technology. Unfortunately, the United States federal government doesn't fund any of this stuff. It's very hard to get funding for this. Yeah.
I have a question. Have you thought about using SWIR as well, or you are limited to the sensor?
Yeah. No, so this is all linear stuff. SWIR is really good. You get better penetration depth depending upon the object. It's pretty well known that you can use SWIR to look at underdrawings and paintings. And so we just did that a couple of weeks ago at a museum in New York City. We had a SWIR camera on loan. Problem with the SWIR camera, it's really expensive, right? It's hard to buy a SWIR camera for less than like 30 grand. But you can use SWIR particularly to look at multiple layers of writing or pigments on things. That's most applicable in the art world. We have SWIR data of the Guff map, but at the time the spatial resolution was so bad, it's pretty useless. It's basically useless. But there is a lot to be done in the SWIR. Yeah.
Anyway, you're studying in these maps, their development over long periods of time. It seems to me there are two hypotheses about what's going on. One is that the world's actually changing and we're getting a record of development in medieval Great Britain. And the other is we're getting a map of our writing down in sophistication and writing down what's happening. Is there any way to distinguish those two things?
I'm a dumb physicist. I can't answer those sorts of questions. But those are the types of questions that these guys are trying to ask, right? So for the Guff map in particular, there's some theory that it was maybe used as a mechanism for tax collection, right? Where do the people live? How many people live in a particular area, right? How do I get from one point to the other, right? There is some evidence that it was probably developed in conjunction with the military, right? The scouts in the military, they're the people on foot running around Great Britain. They know how far it is from one place to another, right? The fact that they clearly started to ignore large parts of Scotland tells you something about what they were trying to do with it. I don't know the details of that. But just think about it. This is an artifact that was in use by somebody in power for 100 years, right? That's like, I'm sure this actually happens, unfortunately, but that's like the US government using maps that were made pre-World War II, right? I mean, think about that, right? Literally somebody was using this map and cared enough to modify it for 100 freaking years. My friend Damien, who works on this over at UCL, he loves to say the Guff map is a graveyard for theories. That's the way he describes it. I don't know. It was on one of my slides. There's a great webpage called guffmap.org, which is hosted, I think, by it's one of the Dublin colleges. I think it might be Trinity College. They did some high resolution imaging of it a long time ago. They built a really beautiful webpage where you can type in like a modern place name and it'll take you to that spot on the Guff map and things like that. If you're interested, that's a great resource. Oh wait, sorry, you were in that.
Okay, wait.
When was the time that Sylvan map was created?
Was created, I think it was late 17th century. So it's like 1690 or something like that.
I have some questions. So on early Qing dynasty, they tried to invade Korea. I think the change in the Korea probably related that invasion. Do you said like there's a color change in that area, like surrounding the Korea?
It could very well be. So yeah, it said what I have here is early 17th century, but I don't think they exactly know, and they don't know where it was made. There's some school of thought that it was actually made somewhere down here in Sumatra, based on some of the detail that's down here, I think. But again, that's not something I really know about. It is interesting though. I have Chinese graduate students, and they zoom in on this thing. They can read it, right? You know, one D-Bai, my PhD student that did a lot of the work on the early stuff, he was super excited about it. He sent a picture of like where he was from back to his parents, right, on the Selden map. It turns out there is some sort of geopolitical importance to this map as China is trying to expand their claims on what is nominally referred to as international waters. This map lays some claim. People can interpret it differently to who owned what when, sort of thing, right? So I don't know. There are a handful of journal articles about the Selden map out there. I would encourage you to go read it because I don't know the details of the history of it.
The second question is that the scope of the research that depending on the change in the carbon in pigments to see when the ton names are changed? Is that like too detailed question?
When did the what change?
Like in either maps, there were the name of the tons were changed on different time. Is there part of the research that concentrated on the temporal changes?
Yeah. That's particular, less for this one. This was probably only in use for a short period of time, as far as I understand it. The Guff map was in use for a very long period of time. And so understanding, one of the interesting aspects to the time is that the historians think that by studying the changes in the Guff map over time, you can learn about what the people in the UK knew about the UK over time, right? What was their sort of broader knowledge of Great Britain, of the island, over those 100 years? Because it obviously changed, right? And so not only how their knowledge changed, but what was important to them, right? In terms of like, they started to ignore Scotland. Okay, fine, we don't care about it. There's people up there, we don't care, right? But some of the other stuff sort of represents their values at the time of what they were interested in knowing. I can't answer any of those questions, I'm sorry. Yeah.
So one of our questions from Zoom, do you have a favorite object that you have imaged?
A favorite object. So the Guff map is always near and dear to my heart. It was the first one of these things I ever sort of worked on, and we know so little about it, right? It's just very cool. I've told some of these guys I'm stepping down as department chair at the end of this summer, and I'm very much looking forward to being able to spend large amounts of time just staring at this thing and applying cool algorithms and stuff like that to it, because we literally do not know very much about it. So that will always be near and dear to our heart. There's sometimes subtle things that you do that are super important. So we have this thing in my program, I have a couple minutes left.
Sure, yeah.
We have a thing in our program called the Freshman Imaging Project, where we require all of our freshmen to spend their first 2 semesters. We give them a problem that we believe can be solved with an imaging system. You have to build this imaging system from scratch, and then you have to show that it actually works come spring, okay? So the sheer look of terror in their eyes in the, first Tuesday of the semester, they're like, what? Pre-COVID, so particularly for the faded text thing in manuscripts, we've known for a very long time that the parchments are organic material. They will naturally fluoresce if illuminated in the right flavor of ultraviolet light. The ink that's been scraped away leaves a chemical mark on that parchment, and so that suppresses the fluorescence. And if you go, I don't know if you guys have a rare collections part of your library here with medieval manuscripts, but if you go in there, they will likely have ultraviolet lights, right? So that you can shine them on the manuscripts to read them, right? So people have known this for a long time that you could do this. The sort of state-of-the-art imaging systems for manuscript studies, a couple $100,000 a piece, 250 grand, whatever. Somebody realized a long time ago, oh, we should put an ultraviolet light on these things so that we can image that. Okay, that's cool. We told our freshmen, we're like, we're going to give you like a few grand, a few $1,000s. I want you to build an imaging system that does nothing but illuminate the ultraviolet and image in the visible, specifically to try to identify palimpsests in libraries, right? That's all I'm trying to do, right? It's a very difficult imaging problem. It's a very low signal to noise problem. You can't illuminate for a long time. There's lots of cool system questions. So they got a very long way to building this system, and then March 17th, the world shut down, right, for COVID. But we were able to identify 3 of them to work during the summer, basically in their homes, to continue to build this thing. They were let back on campus in August, and the first thing we did is we hooked them up with our rare manuscripts collection, and we gave them a manuscript that we didn't believe was palimpsested. But we wanted just to see what would the level of signal off a 14th century piece of parchment be in their imaging system. And they discovered that it was palimpsested. That there was this whole layer of, this thing had been in our collection for 20, 30 years. And nobody knew that it had underwriting. And then it turned out that the underwriting was particularly, the overwriting was really boring. It was just like a choral book or something, right? But the underwriting was actually a letter from somewhere in rural France, from the local magistrate to the local bishop or whatever, because they had captured 3 or 4 prisoners and they didn't know what to do with them. And so by doing that, we're all of a sudden learning something about it. Oh, and by the way, it was such a good palimpsest, right? No, you can't see the writing on it. And usually in palimpsest, you can see the scrape marks, right? Because somebody scraped it with a rock or something. You can't see any of that. So now people are studying that thing to think some dude in rural France figured out a way to scrape manuscripts, and then he was probably selling it as brand new parchment, not recycled parchment. And so the fact that we had a bunch of freshmen that built an imaging system that made this discovery in our lab that turned into a really interesting question. That's also part of what's called the Ege collection. So Otto Ege was this guy at Case Western University in the 1930s. He was a medieval scholar. You would never do this now, but he wanted everybody to have access to medieval manuscripts. So he took his collection of medieval books and he cut them up into pieces. He ripped apart all the books, and then he would create a box that had, say, 5 examples from 5 different manuscripts, and then he would sell them to libraries. There's a really good chance you probably have some here, right? So the leaf that these students studied was an Otto Ege leaf, right? But we don't know where the rest of the manuscript is, right? What you'd love to be able to do is go find the other pages from that same book and see if we can figure out the rest of that story. So we're actively trying to identify other universities in North America that may have leaves from that same manuscript so that we can go see, was it also palimpsested? And can we learn more about that story that was erased away? So there are things like that where it's like totally unexpected. Is it going to change the history of the world? No. But it opens your eyes to a lot of the things that we just don't know. So it's hard to say there's a favorite thing, because sometimes there's subtle things, but they're so meaningful, at least to the students who did it. So I mean, these students got covered in the Smithsonian Magazine for this. So yeah.
Do you know that the Scotland portion of the DOF map was always attached to the bottom? Because if they stopped carrying it.
I don't know why, but they believe that the entire piece of parchment was made first. I don't know the details of that. You can see the stitch marks on the back. I don't know why they think that, but they are very, very confident that the piece of parchment was made first.
So when you showed us the setup of the imaging system, so you told like the platform was in motion. So the map was in the platform and you made the motion so the scanning line imaged the whole map. My question is, why not move the camera? Because if you move the platform with the map on it, it's fragile and it creates a challenge, right? So why not move the camera?
You move that camera, you got a chance it's going to fall. Right? Conservators are very rightly very concerned about the optics. I will not touch any of these things, right? This is something like, I'll set up the camera system, you put your thing down, we'll hit go, and then you take it away, sort of thing, right? I wasn't there when they imaged it. My guess is that the conservators were like, no, you are not dangling a moving camera over this 14th century map. They actually didn't use that system. That the map was stood against a wall like this, still in its frame. And then the camera was put on a translational stage that went this way and up and down, just because it's so big. They didn't want to build an arm that would hang the camera out over the top of it, right? So they did it this way.
So the camera was moving.
The camera definitely was moving in. For that particular case. For the general case with just a manuscript, no, they just slide it underneath there. It's way easier. It's just way easier.
We have time for one more question. Hank? Hank, did you have a question? Okay, so with that, I want to thank David for a great presentation.
Absolutely. Thank you.